Hello, welcome to today's webinar, Using EBSD and TKD for New Insights on the Cold Spray Deposition Process. Before we get started, I'd like to review a few housekeeping items. On your right panel, you'll see a question submission area. You can type in your questions there, and we will answer them as we can. Any questions regarding connectivity issues will be answered immediately during the webinar, and any questions about the webinar will be answered at the end of the presentation. If we don't get to your question, we will answer you via email within a few days. I'd like to introduce this presenter for today's webinar, Dr. Luke Brewer. Dr. Brewer has been developing and applying EBSD techniques since completing his PhD studies at Northwestern University in 2001. After his doctoral studies, Dr. Brewer led the EBSD characterization efforts at the GE Global Research Center in Niskayuna, New York. While at GE, he developed new EBSD methods for visualizing and quantifying plastic deformation and metallic microstructures, and was awarded the Macros Award by the Microanalysis Society for his research in 2002. Dr. Brewer then developed multivariate statistical methods for analyzing EBSD and other microanalytical data types, while at Sandia National Laboratories. For the past decade, Dr. Brewer has used EBSD and other electron microscopy techniques to study complex microstructures formed during metal processing techniques such as cold spray deposition, friction stir welding, resistant spot welding, and additive friction stir deposition. He has been a professor at the University of Alabama in the Metallurgical and Materials Engineering Department since 2015. Now over to Luke.
Great. Well, thank you so much, and thank you to all those who are attending this webinar for your time and attention today. I want to begin by thanking EDAX, and in particular Dr. Stuart Wright and Mr. Matt Knoll for the invitation to come and talk about my group's research on using EBSD and TKD and seeing what it can help us learn some new insights about the cold spray deposition process. I have a lot of people to thank. I have the privilege of talking about our results with you today, but in fact, this is data that has been collected and analyzed and written about by a number of people. I'm highlighting some of the alumni of my group and some of my current students, in particular, Dr. Tien Liu, who's now a postdoctoral fellow at Pacific Northwest National Lab. We're going to talk a lot about her research, and Mr. Christopher Roper, who's finishing up his doctoral dissertation here at the University of Alabama. We're going to talk a lot about his research on austenitic stainless steels. And of course, none of this research can happen without the gracious and sustained financial support of many sponsors, but in particular, I want to highlight the support from the Office of Naval Research and Mr. Bill Nickerson, Dr. Anissa Rahman, and Dr. Jennifer Wolk, and then also for a program that supported the research on stainless steel from the Department of Energy's Nuclear Energy University program. So, as Jonathan pointed out, if you think about the hermeneutic for material science and engineering, which is processing gives us microstructure, microstructure gives us properties, and properties give us performance, my research interest and group lie firmly in the first link in the chain, which is processing microstructure relationships. So we do a lot of research on innovation in metal processing and joining techniques, and then we look at how the micro and nanostructures evolve when we do that, right? So we do a number of different things: metal powder production, cold spray deposition, that's what we're going to talk about today, friction stir processing, casting, and welding and joining. I have a deep and abiding interest in materials characterization. And I mean, you can't make new things and not look at them very closely to see, well, how did they change? And so I've had the opportunity to work with a number of characterization techniques over the years, including electron microscopies, both at the micro and nano scale. I've also used quite a bit of X-ray and neutron diffraction. We'll talk some more about that later today. And more recently, I've gotten involved in atom probe tomography. And this is, I love this picture of my group. It was nice to be able to all get back together again after the COVID pandemic. And but these are the folks that really deserve the appreciation for the work that happens, because I'm just the one that gets to talk to you about it. So cold spray, what a strange metals processing technique. It actually was a bit of a mistake, like many great innovations are. The group of Anatoly Papirin in the former Soviet Union was doing work on supersonic two-phase flow. And so you can see, right, they're doing Schlerin type imaging. Here is the substrate, and they've got their two-phase flow supersonic gas and some metal particles. And they noticed that upon impact that those particles had actually build up on the end of the cylinder. Now, at first, I think there was some irritation about this, but then, like all good engineers and innovators, they realized, wait a minute, this isn't a flaw, it's a feature. So they basically invented the technique of cold spray deposition. So what is it? The long name is cold gas dynamic spraying. We tend to call it cold spray because the other is a bit of a mouthful. It's in the family of thermal spray techniques. And so we see here kind of a map of thermal spray. Here's gas temperature in thousands of degrees C. On the ordinate and on the abscissa, we have the particle velocity in meters per second. So you may be familiar with things like plasma spray or high velocity oxyfuel arc spray. Those are all techniques in which we actually melt the metal particles. Now, they are accelerated before hitting a substrate, but they are molten. Cold spray, the name cold implies that we're actually not melting the particles, okay, at least not completely. And what we're doing is we're trading thermal energy for kinetic energy so that they're moving, a couple times the speed of sound. And so when they hit, you basically have a micro explosion welding event that bonds them more or less instantly. We'll talk more about what that means in a minute, to the substrate that they hit. So here's a schematic from VRC Metal Systems. And so you can see that we use some sort of inert gas, typically either helium or nitrogen. That gas gets heated to increase the expansion ratio. We split it off and pick up some fine metallic powder, say 10 to 40 microns in diameter. And then it goes through, and this is key, it goes through a converging, diverging nozzle, or if you're a fluid mechanics fan, a de Laval nozzle. And that nozzle geometry, which looks and functions just like a rocket nozzle, accelerates those metal particles to supersonic velocities. And again, upon impact, they stick and adhere seemingly instantly to the substrate. And by moving around the nozzle, we can make shapes, right? So this is an example of cold spray of copper onto an aluminum substrate, and you can see that it's basically instantaneous, right? And so this is real time, and you're depositing about 1 millimeter thick worth of material in this particular experiment. So what's great is this is a solid state spray deposition technique, and it can be used to add material to a substrate with relatively little heat input, and that's important for a wide variety of applications. Okay, so let's talk a little bit about what's going on. Here's a nice cartoon by Bay's group in South Korea, where they're kind of showing multiple particles hitting the substrate. There may be some level of embedment that takes place during this process. So when a particle hits, it may in fact partially indent or embed itself in there. It also flattens out. We're going to talk about the flattening ratio here in a few slides. Okay, and then of course you basically build up the deposited material one particle at a time. Now there are many flowing through the nozzle at any given time, but right, it's just impact after impact after impact. And in fact, you can do a simple calculation and estimate that you're dealing with about 100 million to 1 billion particles in any kind of normal deposition. So that's really quite a few. Part of some things that are really crazy are that if you do a simple estimate of the particle strain rate, now it's not uniform strain rate. The strain rate right at the point of impact is much higher than it is higher up in the particle, but you're looking at things that are on the order of 1 million to 1 billion strain per second, which is kind of crazy. The entire deformation impact process takes about 30 to 50 nanoseconds. So that's also really quite something. When I said it's instantaneous, okay, it's not instantaneous, but I would say that 30 to 50 nanoseconds is pretty close to instantaneous. And the average strain, and it's an average strain upon impact, is about 60%, but it can be much higher, again, kind of at this impacting point. So when you consider all that, it kind of reminds me of the famous painting, The Scream by Edvard Munch, right? I mean, like, wow, that's just kind of incredible. So there's a lot of complex deformation physics and mechanics that's going on here that really controls this process. And that's really what we're going to talk about today, is trying to use microscopy techniques to understand what is taking place at between all these impacted particles and during the impact event itself. Okay, so so now I'm going to back up and say, well, why would I care? Why would anybody want to do this? Well, it turns out that cold spray is really being widely applied now successfully in a number of important applications. There's a kind of an approach that I call additive repair by cold spray. You've probably heard of additive manufacturing. Well, in additive repair, you're adding material back in that's been lost to corrosion or wear damage. So here's an example from Australia where they have a magnesium housing, and it had corrosion damage, and say they machined out the damaged material and cold sprayed aluminum back in, and then it can be readily machined back to the original dimensions. Here's another example of a magnesium gearbox, and you can see the areas where they've machined out the corrosion damage, and then they've cold sprayed and machined those areas back to tolerance, and you can keep using those components. So that's extremely attractive. Here's another sequence that shows a magnesium gearbox that's flipped upside down. You're looking at the feet, right, where it's mounted to the floor of the aircraft. You can see the corrosion damage. If that damage is then machined away, you can put a template on this to kind of mask the rest of the gearbox, and you can spray in the missing material. So here we are after deposition, and then here we are, now in the final configuration, and you can bolt this back on and use it again. So that's extremely attractive. That's additive repair. We're actually trying to move. There's a very large program and a part of on solid state structural repair. And so what I showed you before is called dimensional repair. You're just trying to replace missing material. Now we're trying to replace missing material, but we're trying to take structural or mechanical loading credit for it. And there's a number of things that you need to consider in terms of what kind of powders are you using, obviously what kind of spray conditions, what kind of geometries, and then we spend a lot of time looking at the strength and reliability. A lot of these problems are caused by corrosion. So here's a 7000 series alloy from an airframe. You can see the corrosion damage around these fastener holes, right? The fasteners are typically not aluminum, typically either steel or titanium, and that provides the potential for galvanic corrosion as well as crevice-driven corrosion, and then that manifests itself in the aluminum as intergranular attack. So you basically have to kind of get rid of all this material, and then our cartoon way to do this is we go back in and we spray back in that missing material, machine out the fastener hole, and we can use the component again. So those are kind of the applications. More recently, there's a big push on cold spray for additive manufacturing. There's two companies which happen to both be from Australia, which are really making great gains, Titomic and SPE3D. They take somewhat different approaches. Titomic actually moves the nozzle, but using that kind of digital CAD sort of idea that we have for other additive techniques like laser powder bed, but they can build up structures that look like this. SPE3D actually fixes the nozzle and moves the substrate around, and they've been able to make complex shapes such as this cam lock fitting right here, right? So that's very exciting. Recently, we've upgraded the robotics in our own lab so that we fixed our nozzle so we can move the substrate around on a 6-axis robot, again, to give us better control so we can kind of take this approach as well. Nope. Okay. So that's great, but let's go back to the fundamentals. So we decided that there was a lot of fairly violent, very fast things going on. There's a lot of application space, but in many forms of engineering, it's almost our ability to apply the technology has outpaced our ability to understand it. So we're trying to catch up and understand what's going on here fundamentally. And as a metallurgy researcher, I'm interested in how the cold spray process affects the microstructure of the material produced by that process. And of course, ultimately, how does that affect its mechanical and corrosion behavior? Here's an example of 7075, which is an aircraft grade aluminum alloy, heavy on the zinc, heavy on the magnesium. So if you think about a wrought microstructure, you wouldn't see very much at the micro scale. But in cold spray, it all starts with powders, and most of them are made by inert gas atomization. Now, when we look at this powder particle from 7075, we see that we've got dendritic or somewhat cellular solidification. And so these gray regions are the alpha phase matrix, but then you see these bright regions in this backscatter image. Well, those are the intermetallics. So during rapid solidification, you get strong segregation of the solutes, which should be strengthening your material, but instead they're just forming networks of intermetallics, which is not a happy thing. One of the things to keep in mind in cold spray is that we don't really reset the microstructure. So if you used a fusion-based additive technique, well, it remelts the microstructure and then it resolidifies. Now that can cause its own issues. In the case of cold spray, we simply take this little ball that has this microstructure and we impact it at high velocities into the substrate or into another previously impacted particle. So you can actually see the prior particles. We're going to call those prior particle centers. And then you also see that there's regions in between prior particles, and we're going to call those prior particle boundaries, and they have a very different structure. We can readily deposit this material. This is an example at the lower left. It's an optical image of a 7075 deposit on a 7075 substrate. And if I didn't tell you that I'd done that, you might not have guessed. Actually, the substrate looks a little bit worse for wear. You get some some pitting when you polish these samples due to corrosion of intermetallics. But the bond line is almost perfect. We've got better than 99.5% density here. So the process can make excellent material, but has a very complex microstructure. In the bottom right is a map my student Jacob took recently. And again, you see that the highly deformed regions, this is an inverse pole figure map taken by EBSD. You see the prior particles, these kind of larger areas. Let me point at those a little bit more clearly. So these are prior particle centers. And then these very fine looking regions, those are prior particle boundaries. And we'll talk in a moment about what might cause that to happen. So we're going to guide this talk. We're trying to answer three sets of questions. How does the cold sprayed material microstructure differ from raw material, and I would say even from the powder that it started? How is the cold spray microstructure developed by that single particle impact process? That's kind of the unit operation of cold spray. And how does the cold spray microstructure evolve with subsequent heating? So let's take on the first one. EBSD and TKD are going to provide information, particular information that we need to try to answer these questions. So let's go and look at the microstructure we get out of cold spray, and let's think about it in terms of grain structure, in terms of plastic deformation, in terms of texture. Okay, I do want to stop and kind of hit the rewind button for a minute, and let's talk a little bit in case you're not familiar with how EBSD can be used to map plastic deformation. Okay, so we have this little cartoon that I drew a long time ago, but here we have an electron probe that we can move along the surface of the sample. And why we like EBSD, one of the reasons why we like it is because we can locally measure the orientation of that point on the surface. And we can do that in terms of, say, Euler angles. So I have three regions here, 1, 2, and 3, and each one has a measurably distinct set of Euler angles. Okay, well, I can readily calculate the misorientation between these sets of Euler angles. And that degree of misorientation can be related to the arrangements of something called geometrically necessary dislocations, or GNDs. Now, GNDs are a continuum mechanics concept, and it says that for me to describe curvature in a lattice, so a bent metallic or ceramic and any kind of crystal material lattice, that I actually need a set of dislocations to actually enable to describe how I get from one orientation to another. That's why they're called geometrically necessary. Okay. Another way I like to think about it is that if I was to look at the material from a continuum mechanics standpoint, what is kind of the super Burgers vector that I have, right? These are basically large Burgers vectors, and so when I cross them, right, it causes a rotation or a tilt in the material. Now, there are other kinds of dislocations, statistically stored dislocations, and those have a 0 net Burgers vector. So when I march across here with my electron probe, I don't actually measure any misorientation or rotation of the crystalline lattice, but there's still dislocations. So that's just something to keep in mind. There's a difference between the continuum way of viewing dislocations and the metallurgical in the TEM way of thinking about them. So let's just be mindful of that. Nonetheless, I can take this information and I can actually plot the orientation and misorientation information that I get in any number of ways. I can't go through all of these in this talk, but you can see this is an indent, a Vickers indent corner in an austenitic stainless steel. And by looking at different kinds of orientation and misorientation maps, we can actually visualize. I particularly like this one in the bottom right-hand corner. This is a way using kind of local misorientation spread or reference orientation deviation that shows us kind of this plastic deformation region around the corner of that indent and along the edges of the indent, which is what we would expect would happen. Again, I'm just trying to hit the highlights when we talk about some of these maps that for those that haven't done these things that we can stay together on this talk. If you really want to read more about these things, Stuart Wright wrote a great review article with Matt Knoll and David Field in 2011. I wrote a book chapter with David Field and Christopher Merriman in 2009, and I wrote a paper about some of these algorithms in 2006. But here's some work on partially recrystallized steel by Stuart and his colleagues from this M&M article in 2011. And what I want to point out is I kind of think about visualizing and quantifying plastic deformation in kind of 3 bins. One is on a grain by grain basis, so here on the left. So we're looking at what's called grain orientation spread, which is a way of calculating the average misorientation, intra-granular, inside a grain misorientation, but doing it on a grain by grain basis. So every point in the grain after the calculation has the same color, if you will, or value. And so that's called a GOS map, grain orientation spread. You can see that the recrystallized grains are low in orientation spread, right? And so they're blue, and things that are not yet recrystallized have a lot of orientation spread within the grain, and they're colored red. On the extreme opposite, let's go to the right-hand side. On the opposite end, we have what I would call local misorientation. So this is a very popular kind of map, a kernel average misorientation map. It comes in several flavors. This is the neighbor flavor. But in this idea, what you're doing is you're looking at a pixel, and then you're calculating the misorientation between that pixel and its nearest neighbors. Now you can choose how many nearest neighbors you use, but you know there's all kinds of different variants on this. But the general idea is that I take the average misorientation amongst the center pixel and its neighbors, and I assign that value to the center pixel, right? And so locally, regions that have high misorientation will show up. You can actually see kind of these green areas. It's nice at showing, again, these are kind of networks of just geometrically necessary dislocations. And then areas that really don't have any local deformation, well, those show up very nicely as well, right? There's one that's in the middle, which I like. I spent some time developing, and it's useful in the right context. So I kind of go back and forth between all three of these different ways of looking at the data, depending on what problem I'm trying to address. This is called a grain reference orientation deviation map, or in E-axis software, the GROD map. And so it's really a combination. You start with a kernel average misorientation map, and the game that you play is where in this grain, let's do a highly deformed grain, where in this grain do I have the smallest kernel average misorientation? Sometimes it's obvious, sometimes it's not. And then this is, you know, let's outline our grain here. Okay. So then I'm going to take that kernel for my whole grain, and I'm going to map the misorientation of every other pixel with respect to, or in reference to, right, that kernel. And so that's what we're seeing. And so it's really good at visualizing curvature within grains, but in some sort of, you know, in some sort of deliberate way. You have a deliberate starting point, which is you chose the kernel that had the least amount of misorientation. So in any event, we're going to talk about, you're going to see grain orientation spread, GROD, and CAM maps in this talk. So let's keep going. Okay, so now back to cold spray. So it all starts with gas atomized feedstock powders. That's where it begins for cold spray. This is work by Tien. We're looking at aluminum 2 weight% copper, aluminum 5 weight% copper powders. And so you can see, we see a secondary electron image of the outside. We see backscatter electron images of the inside. EBSD allows us to kind of visualize what the grain structure looks like, and we can measure that grain size, and we find that it's somewhere between 2.2 to 2.6 microns for these particles. We looked at more than just one particle, but on average, we got values that look like this. Okay, so what we saw in our feedstock powder was that they had the expected spherical shape you should get, that the powder size range was with 10 to 40 microns. That's quite typical. We looked at the cellular solidification structure. I'm not going to go into that today. And then we also looked at the continuity. This bright phase in this case is the aluminum 2 copper theta phase, and we didn't see any GP zones in these powders. When you cold spray this, of course, the microstructure changes, and we see this core shell, or sometimes I call it a bimodal deformation structure. So here's our prior particle. You can clearly see something like that. Maybe it truncates here, a little hard to see with 1 2D section. In the middle of the prior particle, you have this very nice aluminum 2 copper intermetallic network is still intact in this example. Okay, and this is a TM image, a stem image. But then if I go to this much finer looking prior particle boundary region, well, now we actually see that we've got this ultrafine grain, so 100 to 300 or 400 nanometer size grains. Now they're not equiaxed in this particular example, but you can see in the stem HADF image, right, the ultrafine grain structure that you have. You can also see that we've obliterated the intermetallic network, and so now it's been broken up into nano size aluminum 2 copper powder particles, right? So that's the difference between what I did with my starting particle and what ends up after that impact event in cold spray. Well, EBSD is super useful at kind of doing a better job of both visualizing and quantifying what's going on. And so again, 2 weight% copper, 5 weight% copper. We have an inverse pole figure map with respect to the spray direction, which is being shown going from from right to left in this case. You can see, again, those ultrafine grains in between prior particle centers. And we've plotted both high angle grain boundaries in black, and by that we mean 2 to 10 degrees. And then we've got 1 to 2 degree low angle boundaries. Sorry, we've got 1 to 10 degree low angle boundaries, and then things that are higher than 10 degrees we're calling high angle grain boundaries. And so you can see how that density of boundaries changes both between the two different alloys and with location in the structure. Here's one of those plasticity maps I was talking about. So grain reference orientation deviation, or GROD, and it does a very nice job of showing us that we have a lot of intragranular misorientation in the prior particle centers. So these kinds of regions here, and that we actually have a much lower value of intragranular misorientation in the ultrafine grains, kind of in between in the prior particle boundary region. And so there's two things that we've learned here that are a distinct departure from what we saw in our starting feedstock powder, and it would be very different from the raw material. We see that we have a bimodal microstructure which has 2 to 3 micron sized grains in the prior particle centers and 200 to 300 nanometer sized grains in those prior particle boundary regions, right? And that those ultrafine grains have lower values of intragranular misorientation compared to what we see in the prior particle centers. So those are two takeaways that EBSD really helped us with. And this is just kind of zooming in so you can actually see kind of some of the details. This is pushing on the hairy edge of what we can reliably do with EBSD. And so that's a lot of this black dropout that you see is just our inability to index those regions. We'll look at this using a higher resolution technique in a few minutes. Okay. We've also seen, and there's really not many results on this in the literature, but we actually have seen some evidence for the development of deformation textures from EBSD. Now, to be fair, you could do this in X-ray diffraction or neutron diffraction, and maybe we should. I think those would be better techniques because they're going to average over a whole lot more orientations. But nonetheless, we went and saw what do we have, and we actually did see for both aluminum 2 copper and 5 copper that there was a weak, and it is weak, maybe again, maybe we don't have enough crystal light sampled, but we saw a weak 110 fiber texture, right, along the spray direction. Okay. And we didn't see any particular difference depending on the amount of copper content that we had. I'm kind of intrigued by this. So I've checked it several times, and I can tell you that in some cases we see a fiber texture and in some we don't. Here's another example where we have. This is some work by Dr. Lorena Perez, who works with me. And so recently she published some work on cold spray of titanium. And in the case of commercially pure titanium, we use both nitrogen and helium spray gas. Now let me say a word to those that don't do cold spray. The lighter the gas, the faster the particles go. So there's about a factor of 7 difference between helium and nitrogen in terms of speed, or it's a little bit more complicated. That's 1 over the square root of the molecular weight of the gas. Nonetheless, helium sprays go a lot faster than nitrogen sprays. So you can see an immediate difference in the microstructure. These are inverse pole figure maps. I think actually just in the kind of along the cold spray direction. And then you can see the corresponding pole figures where the Z direction is showing the spray nozzle axis. So for nitrogen sprayed CP tie, we really didn't see any kind of measurable texture, but we did actually see a weak basal type texture for the CP tie sprayed with helium. And so that's an interesting development. We have looked at this for some other materials that we've been studying, some Inconels and steels, and you don't see texture all the time. We've seen it in that aluminum case, and we saw it in titanium, but that's probably a thread that deserves further pulling. Okay, so I'm going to change gears now and go to our next topic. So that's kind of overall what we see in the microstructure. But as we already discussed, this process is really controlled by what happens on the single particle impact, the unit operation. Every time one of these particles hits the substrate and another particle hits it, that's what builds up cold spray. What can we learn from EBSD or related techniques about what's going on? And here's a picture we're going to talk about quite a bit. Notice that this scale bar is 1 micron. So this is pretty small stuff. Here are some backscatter images. This is spraying commercially pure aluminum onto a 4340 steel substrate. And what you can see is that it completely pancakes. So these were spherical particles to begin with, and when they hit, they just pancake themselves. And if you use a focused ion beam, you can kind of cut through the particle and you can see just how flat it is, right? And so Peter King actually developed a way of kind of quantifying this, as did Asadi in Germany. And so it's called a flattening ratio. And so it's 1 minus kind of this distance here divided by this apparent diameter. And in the case of pure aluminum, the flattening ratio is about 90%, right? If you want to, you can think of that as an average strain, right? But it is average, right? So there's quite a bit of strain gradient in these materials. Okay. What about copper hitting steel? So this is copper hitting the same substrate, right? And well, now it indents. You can see how very little flattening we're getting, not a lot. You can also see that it indents. Remember that aluminum was just a flat interface, right? And its flattening ratio is about 0.5. You can see all these divots where particles didn't hit. That's because we were actually doing a particular experiment where we're trying to just get single particles and not a whole coating so we can study them. So the question we had is, well, what happens if you're using aluminum copper alloy? Is it more like pure aluminum? Is it more like pure copper? So we used a whole series of 2, 3, 4, 5 weight % copper samples, and we impacted them. This is looking down on individual impacts. This is using a focused ion beam to kind of cut through one of them. You can see kind of this bond line region here, right there. So immediately what we see is that it's not as flat as the pure aluminum, but it's not really indenting very much like the copper did. So that's kind of an immediate takeaway. We did quantify the flattening ratio for, I think we did, I guess 10 to 12 focused ion beam sections for each one of these. And so these are the statistics that we got. And what you can see is a lot less flattening than for pure aluminum, but perhaps a little bit more quantifiably than we got with copper. But no real statistical difference between the alloy, as a function of copper content. So that was pretty interesting. Also looked at it in terms of how fast are the particles going. So as we increase the gas temperature, we increase the compression ratio for the gas, that increases its speed. And again, we really didn't see any difference. So it seemed kind of hard baked in that we were getting somewhere between 0.55 and 0.6 in terms of the flattening ratio for these particles. Okay, and so now what we're going to do is we're going to look at that interface and say, well, what's going on right here? But that's a really small length scale thing. So how can we do that using kind of similar techniques? Well, there's 2 ways that we could do this. One is with transmission Kikuchi diffraction. So this uses kind of the same basic setup. We've been able to do this on a number of different platforms without really much modification. There's some very specialized equipment out there, but we just kind of use the same things that we normally use with a slightly modified holder. I will say that it can be tricky to not have shadowing on your sample, but in any event, we used a focused ion beam lamella to do this. And we tilted it off of the horizontal by about 20 degrees, and we use our EBSD detector. You do have to completely recalibrate the geometry that you have, right? So EBSD indexing is all about triangles, and your triangles are very different in this geometry than they are at the normal 70-degree incidence going the other way. So you do have to recalibrate carefully, but it can be done. A nice review paper on this was by Sneddon and colleagues in Australia in 2016, if you'd like to read more about that. We also do a fair amount of precession electron diffraction in our laboratory, and so this is using the Nanomegas A-star system. And so in this case, you do conical diffraction, so you actually form a cone out of the beam and precess it. The precession means that I'm precessing around that axis. And what that does is, regardless of sample orientation, it gives you kind of a quasi-dynamic diffraction pattern, right, which you can kind of see here, even if you're not tilted anywhere on zone. And then you actually create a whole set of templates, and it matches your experimentally measured patterns to your template, right? And then it chooses the orientation that's best matched. So we apply both of these techniques to fib lamellae from aluminum 2 copper, aluminum 5 copper, and learn some really cool things. And if you want to read more about the details on this, I think somewhere, yeah. So Tien published a paper in Actimat in 2019, and so it goes through all the details on this. In this case, we're looking at TKD data. So this is a TM bright field image in the upper left, and a STEM HADF image in the upper right. And then we have an inverse pole figure map, I think, just kind of coming out of the board at you, and then kind of an inset here in D of this black dashed box. And then we have a cam map, right, is right here, and we have a G-rod map here in E. So that's good that we talked about what those things are. So one of the things that we noticed is that we actually had the formation of ultrafine grains right at that aluminum steel interface. Okay, as we would predict, as we kind of saw in the SEM in the deposit, this is kind of where these things come from. They come right at that impact site. Okay, they do have low values of intragranular misorientation. I think a lot of times we like to call that recrystallization. I'm going to use quotes on that, and we'll talk more about why in a few minutes. And the kernel average misorientation maps allow us to visualize we are actually getting more deformation in the crystalline lattice as we go from the top of the particle towards its impact site, right? And so that kind of makes intuitive sense, but that does mean there's also a large deformation gradient from top to bottom in a single particle. We didn't see particularly strong differences between aluminum 2 and aluminum 5 copper. There was a little bit of a finer microstructure, grain structure in the aluminum 5 copper than the aluminum 2 copper. Now that might be sampling. We saw quite a large grain in this particular aluminum 2 copper sample, and then finer in the aluminum 5. But from a statistics standpoint, if we were to sample many grains, what would we see? We did see, this is a particularly nice example of that low misorientation, ultrafine grain structure here at this impact site right here in the aluminum 2 copper. So I think that this is a result that wasn't particularly surprising, but it's nice to actually see the data, right? Because it's the first time we've actually as a community really seen this. This was one, again, a happy happenstance. So Tien was looking at single particles, but she found one that was actually 2 particles. And so we've got particle 1, if you will, and particle 2, and the red dashed line is the impact interface between the two. So I don't think she knew that when she was fibbing this out, but when she got in the TM, it became apparent. And part of what's fascinating about this is that, again, we have this ultra fine grain region right here, and then this is the corresponding G-rod. Now this is actually a PED set of maps, precession electron diffraction. But what's fascinating about this is that so the impact of the second particle on the first particle created its own band of ultrafine grains, right? And that had not been seen previously, and it gives us some real insight that we're going to talk about in a moment in terms of understanding what's going on here. So what to think about these ultrafine recrystallized grains? Now, the idea that there's ultrafine grains is something that people have observed many times in the cold spray literature, but we're all still wrestling with, well, how does this come about, right? And I have some thoughts I'd like to share that I think have been given to us by EBSD, TKD, and PED. So one of the things that we realize is the ultrafine grains are generated at the particle substrate interface, okay? And they're also at particle-particle interfaces. Now, this is really key. No subsequent impacts or heating are required. So I think that's something that, there's some talk in the literature about, well, as you build up plastic deformation and you do get some heating during cold spray, which you do, well, that, they kind of think about that almost in terms of like classic recrystallization, static recrystallization, but there's a number of problems with that idea. Probably the most fundamental is that the timescales of impacts are very short, right? Probably 30 to 50 nanoseconds. So you really don't have time for diffusion-based classical recrystallization. Like, how did I get these ultrafine grains in less than 50 nanoseconds? Okay, and so it might actually be the rearrangement of dislocations during this impact event that's actually forming new high-angle boundaries. And there's a great set of papers by Joy Hines and Ken Vecchio from the late 1990s where they were doing work on shock deformation of copper, and they came up with a model that they call progressive subgrain misorientation, or PRISM. And I like that idea. I think there's a lot to it. There's some recent work by Rojas in Canada, which actually did molecular dynamics simulations and saw, it looks great. I was very excited to see this because as the particle velocity, they're basically taking FCC particles in simulation and impacting them on a substrate. And what they found is that at some high velocity, they did actually start to get, right? They call it dynamic recrystallization. So, okay, but we're getting the formation of new ultrafine grains, right? And so I'm very excited about this. I think it's an area that still requires further thought and research in cold spray, but I think combining tools like EBSD, TKD, PED, and simulations, we can actually make some real progress on this. And then just in terms of those, probably there are those who are interested. I'm not going to spend a lot of time on this, but maybe we can ask some questions if you have them later. We have actually done TKD and PED on the same sections, and have kind of, qualitatively, we're able to get similar information out of both techniques. We do notice more artifact issues with PED in terms of indexing ambiguity, and that turns into like island grains that we don't see, like right here, that we don't see in the EBSD, the TKD technique. However, TKD had a lower indexing rate, particularly in those ultra fine grain regions, and we did use the same 20 nanometer step in both of these. Okay, the last thing I want to say before we change topics is that this is, of course, the single particle impacts at the top that we've been talking about. We saw that there was kind of more plastic deformation closer to the interface, but it is clearly heterogeneous. What we found is that when you have repeated particle impacts, so now the bottom are actual coatings, and these are kernel average misorientation maps, that when you look at the distribution of intragranular misorientation, it's much more uniform after repeated particle impacts. Okay, third and last topic is to say, well, what happens when you heat these things up? And so we're going to change topics and materials at this point. One of the projects that we've worked on the last several years, and Christopher Roper, this is kind of the core of his PhD work, is funded by the Department of Energy Nuclear Energy Program. They store spent fuel in an above ground storage cask. So this is a big stainless steel cask to store spent fuel. And they're often in near coastlines or maritime environments. And they have welds because they're stainless steel and they're welded together. And you may know that you can get large tensile residual stresses in the heat affected zones of austenitic stainless steel welds. It's also possible to get sensitization in those areas, and that combined with the salt mist atmosphere can lead to intergranular stress corrosion cracking, which is not good. And so there's a large effort with many institutions trying to figure out how to repair these welds in situ, right? Or at least do preventative maintenance or both. And so one of the things that we've looked at, and we're going to talk about laser assisted cold spray today, and we won't talk about additive friction stir deposition, although my colleagues and I have been working on that here as well. But let's talk about what laser assisted cold spray might do for us. First of all, let me acknowledge that we already know how to cold spray austenitic stainless steel. That's a known thing. There's a couple dozen papers in the literature that talk about that. Here's some work from France by Codet, and they showed that they could cold spray stainless steel. In this case, I think it's 304. But here's what we learned, and that is that if they made tensile samples from their cold spray material, and they loaded them up, and they have very little elongation to failure. Okay, so it just kind of loads up elastically and then fails. Well, then they went ahead and annealed it at 400 degrees C for 4 hours, and it loaded up and it failed. But when they finally got to high enough temperatures for long enough times, it actually resets the microstructure. So now you actually get elongation prior to failure. And you can see that in the scanning electron micrographs. You see the microvoid coalescence, which is indicative of ductile failure. So we're trying to figure out, well, they had to do this in a furnace. We can't very well put that entire cask in a furnace. Can we take the source of heat to the cold spray repairs on welds? So that's what we've been trying to do. This is the laser assisted cold spray system that we have in our lab, and you see a little movie of it in operation. And that allows us to either use laser heating while we're cold spraying, or as we're going to talk about, to do in situ laser heating after we've cold sprayed. So here you see we did a set of experiments where we used cold spray to make 304 stainless steel deposits that are, say, 2 inches long by 1.5 inches wide by 2 millimeters thick. We used in situ laser heating with our optical pyrometer to maintain either a 750 degrees C or 950 degrees C surface temperature. And then we did one single pass to recover the entire surface, moving in at 10 millimeters per second with the laser. And the spot size is about 8 millimeters by 6 millimeters. And it gives us, and this is important, a total irradiation time of 85 seconds. Okay. So you can see some suggestion in backscatter images of maybe some changes in the microstructure. You can certainly see changes in hardness. The one that was heat treated at 950 C is definitely softer. And you see the cold spray material is higher in hardness. And the 751 is higher in the first millimeter in hardness, and then it softens in the top millimeter, and then it goes back to its previous hardness value at a depth of 1 millimeter to 2 millimeters. Well, EBSD kind of gives us some clues about how things are changing. So these are inverse pole figure maps with Z coming out of the board. The no laser or just cold spray materials have the classic cold spray microstructure. You have kind of prior particle centers like this, and then you have the prior particle boundary regions, and it's hard to reliably index them because they're tiny and highly deformed. But when we do the laser heating, Now we can actually see all those smaller grains, but the bottom half, which had that higher hardness, it still looks like a cold spray microstructure. But the material that was heated at 950 degrees C surface temperature, well, it's fully recrystallized, and I'll show you more compelling evidence in a moment, but certainly the microstructure has transformed, right? The grain size and shape is different. If I didn't tell you it was cold spray, you probably wouldn't even guess it was cold spray. And we see quantitative grain size data measured by EBSD that in fact supports the observations that we see qualitatively. So this is where we can now use the grain orientation spread algorithm that we talked about at the beginning of this talk to kind of give us a better handle on what's going on. So again, this is looking at the amount of intragranular misorientation on a grain by grain basis. Things that have a orange or red color have higher levels of deformation. Things that are blue have lower levels of intragranular misorientation. And so you can see, and I just love this particular image, B, at the upper 1 millimeter of the 750C, you can actually see necklaces of recrystallized grains that are starting to consume the more highly deformed prior particles. And so that's really great. For 950C, you've pretty much recrystallized the entire material. Okay, well, that was EBSD. I'm a fan of using more than one technique to solve complex problems, just to make sure that we're thinking about it the right way. So we partnered with colleagues in Hungary, and we did monochromated X-ray diffraction with a laboratory system, and we combined that with a very elegant convolutional multiple hole profile way to fit the entire X-ray diffraction profile that we have here. You can see the residuals, so it's very high-end fit to try to account for all the different sources of broadening that we see in diffraction. And you can actually develop a dislocation density metric using this approach. And here you can see that we have a high dislocation density in the cold spray material where we're not using a laser. And then you see that the top half of the material after a 750 degrees C laser heat treatment is definitely a much lower dislocation content, but the bottom half still, there's actually no discernible difference with the cold spray material, right? You also see a change in the diffraction domain size, which for the sake of time, I'm not going to go into today. We also have been doing neutron diffraction at Oak Ridge National Laboratory to kind of further corroborate, get kind of a larger volume of sampling, right? And so again, now I don't have data to show you today. We've been doing this recently in situ, and we see the same things in situ, but it allows us to measure the kinetics. But these are kind of for single deposits. And again, you can see both looking at full width at half max of the reflections, or using the CMWP method to actually calculate dislocation density. And you can see for cold spray, highly deformed, and then substrate, boom. You can see with 750C that you're starting to get rid of that dislocated structure, but then you weren't completely successful, and then you hit the substrate again. And this was good, because we didn't realize this without the neutron diffraction. Even at 950C, you get rid of most of the dislocated material, but not all of it, right? There's still some left right at the interface with the substrate material. So why is this going on? And I'm almost done. I've got about 2 slides left. So why is recrystallization so rapid in cold spray materials? And by the way, we've also seen this in Inconel alloys. We've seen this in a number of different instances, and I'm kind of fascinated by it. And you know, how is EBSD helping? Why do we need EBSD? Well, X-ray and neutron are great techniques, but they're averaging over the entire microstructure. So we can see on average what's going on, but we can't tell you where things are taking place, or perhaps how they're proceeding in the microstructure. Recrystallization is a diffusional-based nucleation and growth process. And so the idea is that I have to nucleate recrystallized grains, and then I grow the recrystallized grains. And this is this is kind of some of the original data on this topic from 1945 from Anderson and Mell on aluminum. And so the hypothesis that I would put forward today is that I think the ultrafine grains that we produce in the cold spray process may actually allow us to skip the nucleation process and go directly to growth. And that's why we can do this recrystallization in 85 seconds, whereas if you follow the ASM heat treatment schedule, it should require, you know, the better part of an hour, right? And so I think it really has to do with the fact that you fundamentally change the nucleation and growth requirements on recrystallization in cold spray materials. But that's a hypothesis. So just to conclude, we've used EBSD and TKD to provide new helpful insights on the cold spray deposition process. We've learned some new things about the bimodal nature of the microstructure with larger, highly deformed grains in prior particle centers and ultrafine recrystallized grains at prior particle boundaries. We looked at some detailed work on single particle impact interfaces and used TKD and PED to do that. And we found that it's the impact event that causes those grains. And then last, we looked at how in situ laser heating can cause rapid, complete recrystallization in cold spray microstructures. And EBSD is really key for allowing us to see where that takes place and how it progresses. And so with that, thank you very much for your time and attention today. And again, these are the instructions about how to put questions in if you have questions about this talk, and I'll be happy to spend some time now answering them. So Jonathan, at this point, do I turn the Q&A back over to you or Stuart?
Hi folks, this is Stuart Wright. Thanks, Luke. That was a great talk. There are some really good questions that I think you'll be able to answer pretty quickly. How thick is the thinnest ceramic substrate you think you can coat, and what is the thinnest possible coating that you can achieve?
Okay, so let's do those in reverse. So the thinnest possible coating, in a sense, it's set by the powder particle size, right? So our powder particles are somewhere between 10 to 40, 45 microns in size. And so I'll tell you what, yeah, perfect. So, right, this is what particles look like in a coating, or actually, I think the cartoon by Bay is even better. There you go. All right. So depending upon the properties you require from the material, it's going to set the minimum thickness that you can make, right? So this is 1, 2, 3, 4, right, in this cartoon, 4 particles. So that would be, say, on the average, if each one of these is, say, 20 microns going this way, well, that'd be about 80 microns. And so if it's less than that, you'll start to have problems with coverage, right? It becomes a statistics problem at that point. So I would say rule of thumb, trying to dip below about 100, 150 microns is going to start to cause property issues, but you should be able to get down to 100, 150 microns fairly easily. In terms of ceramic substrates, to be honest, I haven't done a lot of work on ceramic substrates. So I kind of have to think about that. The key would be the adhesion. So how well do these impacting particles actually adhere to a ceramic material? And I haven't done a lot of that. I've done almost exclusively metallic depositions on metallic materials. I think I've read some literature where you can put down thin layers on ceramic materials, but adhesion is going to be the key concern.
Couple other questions. Do you get oxides formation in the particle interface?
Sure, great question. So you do not get oxide formation during normal cold spray. I've not seen that. And again, so in this work on single particle interfaces, we actually went in and did high-res microscopy, TEM and some microanalysis. Where is that now? Sorry. Right. So when we analyze this, at this interface here, different, and this is pretty interesting, at the very nanometer scale, so we're talking about less than 5 nanometers, depending on what the participants are in this impact event, the literature and in our own results, we've seen both intimate crystalline contact, but we've also seen about a 2 to 5 nanometer amorphization layer. And that amorphization layer can be a mixture of the metals themselves, but also carbon and oxygen. Perhaps some of that came about as a part of the TM sample prep process. One would have to be mindful about that, but I have not seen oxidation from cold spray. However, when you do laser assisted cold spray, when you go to those highest temperatures, like 900 degrees C plus, we have seen some local oxidation in that regard. Not so much during the impact event, but when the nozzle moves away from the material, it has, a few seconds or tens of seconds to oxidize, and now you're kind of depositing back on that. So for those that want to do laser assisted cold spray, you'd want to be mindful about oxidation, particularly for oxidation prone materials.
Several questions about sample prep. Most of these are cross sections via fib. Is there any other way to do sample prep for EBSD of the particles?
For single particles or for deposits?
Well, I had one question about cold spray, just in general cold spray samples, and then one about basically what's your sample preparation, and then is it fib only?
So, okay, so in terms of cold spray itself, let's focus on one here. Yeah, so Jacob did a particularly fantastic job on this recently. These are actually all in metallographic mounts. and we follow kind of standard metallographic procedure. One of the key things in EBSD is to finish. We find that finishing with vibratory polishing is really important. And so doing a careful job of vibratory polishing is really kind of a key thing. But these are all mechanical metallography based samples that you're seeing of the actual deposits. That's also true for these particles here. So we tend to change up. We use kind of special epoxy when we're doing this, but we'll basically mix powder into epoxy and then cast it into a mold and then do mechanical metallography. Again, that vibratory polishing with say colloidal silica is really kind of a key final step. But that seems to work fine. In terms of the single particle work, that's all focused ion beam developed, because it would be, I'm not quite sure how you would do the single particle work without a focused ion beam because of the site-specific nature of it, right? So this is, it's not clearly labeled here, but I think this is about about 5 micron scale bar here. So as you're trying to cut across this particle, you know, you're probably going to need to do that with a focused ion beam. You could try it in cross section, but it'd be rolling the dice. You'd have a lot of dud samples if you tried to do that as a cross section, just mechanically.
Have you tried broad beam ion polishing at all for cross section?
I have not, because I don't have a working broad beam ion polisher, but I would love to try that, and I think that could probably work really well. In a couple months, we're going to have a plasma fib here, and I'm quite hopeful that the plasma fib will allow us to maybe have some added gains as well. But yeah, I think broad beam ion polishing would be a great way to try.
Question about strain rates and impact. Why don't you get a formation, or do you get a formation of amorphous metal at all?
That's a great question. So the short answer is I don't know. The slightly longer answer is, sorry, trying to go back to where I was talking about that. Yeah, so, and by the way, this is kind of a crude estimate, although I have to say I keep seeing these numbers pop up throughout the cold spray literature, so I don't think I'm that far away. And there are people that do detailed mechanics simulations of this process, and they kind of arrive at this kind of range of numbers as well. There are those that predict, and maybe even some limited observations of evidence that shows potential localized melting, particularly those that ascribe to an adiabatic shear instability model, that you get very localized heating. But in all the work that I've done, I see crystalline material. The only time I have seen amorphous materials when we did that Tien work right at the interface between the aluminum and the steel. And like I said, it was about a 2 to 5 nanometer amorphous region. Interestingly enough, at the same length scale in the aluminum to aluminum interface impact, it was completely crystalline on both sides.
Here's an interesting question. What do you think is happening in that first, 50 nanosecond, or that, instantaneous part of this? Could the recrystallization be happening? Is it happening then? Is it happening after the impact, since the heat dissipation probably isn't instantaneous? Could it be some stored deformation that would create that?
So my current view, and these are just my views, it's a hypothesis, but I feel the more data I collect, the more I feel this is probably the case. I think that the nucleation of recrystallized grains, that band of ultrafine grains, happens definitely within that 30 to 50 nanosecond impact. I feel quite confident about that, right? So this stuff right here is caused by that impact event, because you just, in your experiment, you have one particle impact and you moved away. That was it. So that's the only opportunity that you have for that to happen. And again, I think that by looking at the work of Hines and Vecchio and Rojas and colleagues in Canada, I think what's happened is you're rearranging, it's a fair amount of plastic deformation that's required for this event. I think the dislocations are simply rearranging themselves right into these new grains. And so it's really based on grain rotation and dislocation rearrangement. Now, if you have, because you still have quite a bit of plastic deformation in this region of the particle, if you continue to have heating, could you have those grains kind of start to grow into that region? Well, you could. Of course, we still see those regions in full-on deposits. So it's obviously not enough thermal energy to just completely recrystallize the material. But I definitely think that those bands of ultrafine grains are caused by the impact event itself.
Okay. Do you see a temperature increase in the coating or the cold spray?
Yes, you do.
Okay.
Absolutely.
Okay.
And
Another question about. Oh, sorry. Go ahead, Luke.
I was just going to add a little bit more information about that. It can get to the point of being metallurgically relevant. So for 7,000 series alloys or precipitation hardened alloys, you can get enough thermal input if you're not careful that you start to actually evolve the precipitates in the deposit, but more importantly in the underlying substrate. So they don't call it cold spray because you want to touch it. They call it cold because it didn't melt the material on the way down.
Okay. In terms, another question, follow-up question to the sample prep. Are those cold mounts or hot mounts?
We typically use hot mounts for the coatings, and we use cold mounts for the individual powder particles because it's a different kind of epoxy.
A follow-up comment about the polishing. Someone has piped in that the multi-beam ion polishings do work well for those cross sections, so for big areas.
Do you think they mean, when they say multi-beam, do you think they mean broad beam, or I don't quite know what they mean by multi-beam?
I think they mean the broad beam.
Okay, yeah, that's good to know, because I think that's a great idea.
There's quite a few questions. I don't know where to stop and where to continue. Lots of good questions. Let me try a couple more.
Sure.
Are there any effects from the thermal gradient between the region heated with the laser and the rest of the material?
Yes. Yeah. So right. I can melt my substrate with the laser that I have, right? So it's a 4 kilowatt laser, and depending upon how much power and the spot size, I mean, we can melt things, which we don't want to do. So ironically, you know, early on, cold spray was very attractive in part because of its limited thermal heat input. Now you're actually increasing the thermal heat input. It's really all about control. And I think one of the biggest areas we're working on this actively in my group is on understanding and controlling the heat transfer process during laser assisted cold spray, because you can in fact get carried away for sure.
Let me ask you one last question. I know you've got to run, Luke.
Sure.
Someone has piped in. As far as I understand, Al2Cu copper exhibits very little plasticity. What enables it to plastically deform during the cold spray process?
It's a good question. I don't know that it is plastically deforming per se. So if we go back up here, right? So this is one of these aluminum 2 copper ones, and so you can see that, you know, in the middle here, if I didn't tell you that this was cold spray, and this is kind of like right from the middle of one of these powder particles, it's not, if I showed you this image without context, you might not know that this is in a cold spray material. You might just think, well, it's in the powder. But clearly the level of plastic strain in between particle impacts, well, it just shatters it, right? And so you can see that all these little bright areas used to be one of these networks, but now it looks like this. So I mean, if it's plastically deforming, it's certainly not very much.
All right, thanks, Luke. We'll answer the rest of these questions via email. But thanks for those who have asked such good questions, and thank you so much, Luke, for this presentation. I'll turn it back to Jonathan.
Great, thanks for the opportunity, Stuart.
Thank you all. This will be available on demand to you by tomorrow. For those of you that attended, anyone who registered and did not attend, it will be available next week. Thank you, Luke, and thank you everyone for attending.
Bye.
Thanks, everyone.